Okay, let's hear it.
Okay, so for homework number 5, problem 1, it's asking about the relative humidity, and you have to like look at the psychometric chart.
Yeah.
And I'm just confused. I was looking at your answers and I tried to get the same thing, but I'm confused where you got the humid in 200 grams of pounds of dry air and the 38 grams of pounds of dry air. Because I know that you look at the amount of water because you find that in your solution, but I just don't know how that when you're looking at the psychometric graph where to find the humid in and humid out.
Okay. So I have what I have on hand is the psychometric chart for for the practice exam.
Okay.
So it'll be the same information. We might have to do just a little bit of translation from Fahrenheit to Celsius, but it shouldn't be too bad. Okay, where do we have homework 5? Let me see the question again. Where are you at homework 5?
Like I understand how you like convert to get the amount of water, but when you have the water being like 5.83 times 10 to the fifth, I don't understand like how you can look at the graph with that.
So in terms of, okay, so the first one here is we got to look at the inlet conditions. So it's 90 degrees F, which is, I guess this isn't degrees Fahrenheit. So the first condition, I'm trying to juggle a bunch of screens here, is that we have water at 90 degrees Fahrenheit and 95% relative humidity. So if we look at our psychometric chart, 90 degrees Fahrenheit and then 90% relative humidity, it kind of runs out a little bit on this chart. So if you can imagine this going up here a little bit, right? That would put us somewhere in this mark over here,
Yeah.
And so we have the grains of moisture per pound of dry air. So it's not grams of moisture.
Oh yeah. That's totally
Grains.
what I meant. Yeah.
Yeah. And so if we were to get to this point and draw down on that chart, it would be 200. I think I have one on the Canvas page that has that information a little bit better. So that's one source there. And then the outlet conditions are 40 degrees Fahrenheit. And so that would be 40%. And just based on the mechanism, that would be at 100% humidity. So we can go to 40 and 40, so 100% humid, and we draw down, and that would be this other number here, that's 30 something.
Okay.
Does that make sense? Does that answer the part of the confusion?
Yeah, I guess I'm just confused because like the 5.838 times 10 to the fifth grains of water per minute is like different than the chart unit wise, right?
Yeah, so what we're looking at here is we're going to be having a humid airstream coming in, right? And this is 90 F and 95% relative humidity. We're going to have our dehumidifier, and then we're going to be removing some water, and then we're going to be leaving at 40 degrees and saturated. So
Yeah.
now what we need to do is convert between the volumetric flow rates coming into the system, right? Volumetric flow rate out. So for dry air, that's the same. And so that's why the psychometric charts do everything on a basis of per pound of dry air. And then we can we need to convert the volumes into mass flow rates. And then we need to do a water balance. So that rate of removal then is telling us from, if I check my solutions, make sure I'm not leading you astray here. Stop annotating. Okay, there we go. So if I look at the solutions, and let me just share that solution now. So we've got the humid air in 300, humid air out has 38, and then we are doing a, so where do I get this grains of H2O per minute?
Yeah, so I thought that you would use that to, and the temperature on the chart to find the humid in and humid out. So that's why I was confused.
Yeah, so in this problem, the starting point here, so I kind of jumped the gun a little bit in the calculations, right? Because I converted how much water we want to produce first, and then I converted that into these units of grains just to make my life a little bit easier. But I could have also just converted these grains into a different unit as well, right? Using the density of water.
Yeah.
So this is just some unit conversion playing around with, and then converting the volumetric flow rates to mass flow rates and then back to air volumetric flow rates, right? So I want 10 gallons per minute. So I need to know how many grams or pounds of water that is. And then I need to figure out how much flow rate of dry air do I need in order to get that amount of water being produced.
Yeah, that makes sense.
Is that good?
Yeah.
Perfect.
Thank you.
Questions.
I had a question. I had a question on the ternary charts.
Yes.
So if we have a point that's in between two pre-made tie lines,
yeah,
and we're trying to find the composition of the two phases, like on the sides, like kind of how we had on the practice exam.
Yeah.
Are we just doing like a vertical lever rule there and then applying that to each side of the two-phase region?
Not quite. So let's just pull up the practice exam right now. Here it is. We'll go to this one here. So how they do these experiments, that I think that helps to sort of understand why are we doing what we're doing. So what they do in these experiments is they make up, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different solutions. So they take a jar and they make up a ternary solution with these compositions here, right? So they have a certain amount of A, a certain amount of B, and a certain amount of C, okay? And then they shake it up and then they let it phase separate into two phases, phase 1 and phase 2, okay?
Right.
Then what they're doing is they will measure the composition of phase 1. So they get the mole fractions of all the species in phase 1. They get the mole fractions of all the species in phase 2 and phase 1, okay? And then they plot those values. So for this one here, right, they measured phase 1 is this and phase 2 is this. And then they do that for all of the measurements that they've made, and it allows them to draw this phase boundary here.
Right. And so if we have like a point that's in the two-phase region that
so let's, for example, here.
Yeah.
Right. Yeah. So in this circumstance, what you want to do is you want to draw a new tie line that is the same distance from each of those two lines, but at every single point.
Okay, so then at our edges, on the edges of the two-phase region, we would make sure that the distance from the top part and the distance from the bottom part is the same percentage as it was at our original point.
Yeah, so let me choose a point here that's maybe a little easier. So let's say right here, okay? So we're most of the way to this bottom line and we're pretty far away from this top line. So we wouldn't necessarily want to draw a line that's parallel to the bottom or parallel to the top. We have to draw a line that stays the same relative distance between these two. So like I would say, like if I drew a line perpendicular between these 2 points, right, it would be a little bit further away because it's fanning out. And here they're fanning in, so it's going to have to be about the same distance from that one there. So you would draw a new line that kind of follows that same fanning type structure.
Okay, that makes sense.
Good.
Yep, good.
All right. And then on this one here, the last little thing is you kind of have to interpolate between these points here as well, right? Because that's how so it's almost exactly the same thing of how you're plotting PXY and TXY diagrams, right? So you're choosing 5%, 10%, 15%, and then you're connecting all of those with lines, right? And that's how you're plotting it. So it's the same idea, but they're doing it in the laboratory, actually measuring the compositions of the two phases.
Okay, that makes sense.
And that's exactly how they make non-ideal PXY diagrams as well, is they create a solution, they have a vapor, they have a liquid, and they measure each of the two compositions, and then they plot those two compositions as a function of the pressure, and then they can connect the dots. And that's how you make those measurements as well. And that's exactly what we had on the practice exam for a non-ideal mixture. I gave you a bunch of X's and Y's, and then you plot them versus the pressure. The Y's versus pressure gives you dew curve. X's versus pressure gives you the bubble curve. So that's how they generate these phase diagrams. And so you don't actually need to know how much of each of the two phases there are, because you can work that out after the fact once you've created the phase diagram.
Okay, gotcha. And
All right. Yeah.
I had just one other question. Is there ever going to be like I don't know if this is too general, but is there ever going to be an instance where we will absolutely need the Rachford-Rice equation to be able to solve a system?
So that one is really only going to be useful when you have so you could do it for two components, right? But there's a lot easier ways to solve it for two. The Rachford-Rice is useful when there's more than two components, and it would require a nonlinear solver or a guess and check or an iterative scheme to solve it. So I would not say that's a high priority to memorize how to do on the exam, because I try to avoid nonlinear solvers being required on the exam questions.
Okay, awesome. I appreciate that.
Okay. Questions are welcome.
Sorry, one other question. If we need to use the Virol equation or SRK equation, will we be given that on the exam, or should we include those on our note sheet?
You'll be given that, yeah.
Okay, awesome.
So I'll be giving you any equation that you need to use to solve it, except for really simple ones like, but if it's something like Raoult's law, I'm not going to give you Raoult's law. I mean,
Right.
If you really, really begged me for it, I'd probably tell you what it was on the exam, just because it's something that you've all used a bunch of times. But something complicated like the Virol or Raoult's law, I don't have it memorized. So I'm not expecting you guys to have it memorized.
Okay, awesome. Thank you.
Mhm.
I have a question about the psychrometric chart.
Yeah.
So I guess for any of them, you know how yesterday you talked about like how you find I think the relative humidity with the wet bulb temperature and the dry bulb temperature, but you
Yep.
went like diagonal with the wet bulb. Like
Yeah.
why did you do that?
Okay, so this is a very good question. And I think it's really helpful to highlight the fun and challenges of engineering charts. Okay, so what they try and do on a well-designed chart is they try and make it obvious. Okay, so the dry bulb temperature here, let's say we're looking at this point here, 60. So the 60 is aligned on an axis that's a straight line, right? So it's kind of clear then that this number 60 is referring to this line that's coming out straight out of the axis, right? That's what we kind of expect normally. Likewise, for this absolute humidity, right? It's drawn on another straight line axis, so perpendicular to it. That corresponds to the line we care about. Now, in any engineering chart, we just need to get two lines to intersect. Some of them are nice and straight because that's the decision that is made when you're designing the chart. So like a TS diagram that you may have used in your thermodynamics class, this is oftentimes used for the Rankine cycle. A HS diagram is used for refrigeration cycles a lot of times. So in this case, the T and the S would be your dominant axes, and the H and the S, those would be your dominant axes. So those would be the straight lines. Now, everything else in thermodynamics is not necessarily a linear function of everything else. And so then some of the lines have to be curved. So let's go to the, which you mentioned, the wet bulb temperature. So in the wet bulb temperature, right, we can see that it's curved and the line is curved here. And so coming out kind of perpendicular to these curves here, following along the same kind of idea, right, the lines should go out kind of perpendicularly to the actual measurement. So the 55 line is this one here. So if I had 60% dry bulb and 55% wet bulb, that would put me at a relative humidity around 70%. Now for the lines, yeah.
When you say percent, you mean temperature, right?
What?
When you say percent, you mean temperature, right?
Hold on, let me see. Let me say that again. So 60-degree dry bulb, 55-degree wet bulb would result in a relative humidity of 70%. Did I get that one right then?
Yeah, that sounds better. I thought though the line goes straight, and I'm probably wrong, but I'm just making sure. How do we, I guess you're just telling us on this chart, but like in general, how do we tell? Because there's like lines going in all directions. And when I did it in, I don't know, this is from the practice exam. When I did it on here, I got the right answer, but I didn't do it slant, like going from the 55, I didn't do slanted. I did like straight across, if that makes sense, like 90 degrees.
You mean like this?
Yeah,
I have to double check that. I'm pretty sure.
That's also what I did too.
Okay. Let's see, you know, maybe I'm screwed up here. Let me circle back to this one here, because I might have this one screwed up. And we can double check this. I can double check this pretty quickly just by looking at what the vapor pressure of water is at these temperatures, and we can verify this. So hold that thought for just a moment. But the other lines, I think, are pretty well labeled here, right? The lines here and these lines here. So yeah, I think, let me double check that. So we can either keep on going with questions, or I can just quickly verify which one of these is the right approach.
I have a quick question that's related to a different problem, if
Okay.
you're able to answer it. So on the problem that had to do with ammonia, the Haber process with the ammonia, so it says in that problem that the gas phase is fully saturated with ammonia. And with some help from some peers, I came to the conclusion that we have to make the assumption that X ammonia is equal to 1. Would we still make that assumption if the hydrogen and nitrogen wasn't supercritical?
That assumption is good when the gas phase is supercritical.
Okay, so it's only when the gas phase is supercritical, and that's because none of the gas is going to dissolve in the water or in the liquid.
Yes. So when you have a situation like that, that's going to be a really good scenario like that. So, sorry guys, I'm trying to multitask here. I'm looking at vapor pressure of water.
Okay.
But yeah, so when you have, so if it's two subcritical fluids, right, things that can condense into a liquid, right, but that's usually an approximation we'll make with respect to air, right? In this case, the nitrogen is more or less air, so that simplifies it down so you can assume that there's no air dissolving in the ammonia stream. And so then that simplifies it to the humidity problem.
Okay, okay, so it's not the wording fully saturated that makes us make that assumption. It's the supercritical part that kind of correlates to that assumption.
So the fully saturated corresponds to being able to use Raoult's law to solve the problem. So if it's fully saturated, that means it's an equilibrium thermodynamic condition.
Okay, okay, awesome. That makes sense.
Okay, so I got the vapor pressure here. So what is this chart drawn at? This is, I think, assuming 1 atmosphere. So that's 101.3.
I have another question related to that, what
Yeah.
he was just talking about.
Yeah.
In that same problem, when it's saying that you can assume that the liquid stream from the condenser is 100% liquid ammonia, and then the gas stream is fully saturated with ammonia, is that meaning the same thing?
Let's share that one here. So in this problem here, okay, so in the Haber process, ammonia is synthesized by reacting hydrogen nitrogen. Condensers used to cool the product and separate the ammonia. As hydrogen are gases, supercritical, assume that the liquid stream from the condenser is 100% ammonia. The gas stream is fully saturated. The condenser operates at 25 degrees C and a pressure of 20 megapascals.
Like that's pretty much repeating the same thing, that X is just gonna equal 1, right?
Yeah, and in
It's
this case,
gonna-
I'm explicitly telling you that X equals 1 by saying that
Okay.
the liquid stream is 100% ammonia. So 100% would be a mole fraction of 1. So
Okay.
yeah, so I'm giving you, I guess, the same information in 2 different ways.
Yeah, I just didn't know if it was meant the exact same thing, or if
Yeah.
I was supposed to pick up 2 different things from that. Okay.
No, so it's the same thing, just repeating it to
Yeah,
make it crystal clear which approximation I'm looking for.
makes
you
sense.
to do.
Thank you.
Okay. So. Any more questions? So with respect to the psychometric chart, I'm getting flashbacks that I've had this discussion before. I'm trying to think if there's a way I can suss it out really quickly just to verify. But I've got that I guess I could just work it out with you guys right now to show you my thought process. I'll just work it out on here. Okay, so I looked up that the vapor pressure of water, annotate. This is highly compelling content. P star at, let's choose, I just looked up 60, was equal to 1.8 kilopascals. So 1.8 kilopascals. And we need to know what relative humidity this is. So the mole fraction of water would be equal to 1.8 kilopascals divided by 101.3. And that is 1.8 divided by 101.3 is 1.8% equals 0.018. And this is number of moles of water divided by number of moles of water plus number of moles of air. I choose 1 mole of dry air. And then we can solve this one here for the amount of water. So I'm trying to get this to an absolute humidity. But I can use that because that one's an easy reference state here. Solve X divided X plus 1 equals I probably could have just not worried too much about that. NH2O is 0.0183. So then I need to convert this to pounds. Geez. Pounds of moisture per pound of dry air. I know what I can do. I can look at the ratio. 1660 here. Oh, geez. It's just a lot of tinkering work. Molar weight of, so the molecular weight of water is 18. This is moles. This is grams per mole. So I need to times this here. So that's 0.0183 times by 18.32.0.33 grams of water. Molecular weight of air is 29. So then we have grams. This is grams per mole. I have 1 mole, so that equals to 29 grams of air. And so then the ratio, pounds of moisture per pound of air, would be the same as grams of that. So 0.33 divided by 29 gives me 0.113. Okay, so 0.11, so that's here. And I draw this one up. A little bit off. Okay, maybe my math is not, oh, that's 100% saturated. So that doesn't help because I need to do it at a percentage saturation. Okay. Well, is there questions, or do you guys just want to watch me suffer through this calculation here?
Oh, so will this like type of question be on the exam?
Yeah,
Because
I was
that's
aiming to
something-
have a psychometric question beyond the exam, so I want to clarify
like-
this, particularly if I
Okay, so
watch
it
it.
could be on the exam, but like, would it be related to the wet bulb temperature or anything like that? Because if it's
I
not,
can
then
make
it's-
I can make it so it's not related to the wet bulb temperature. I don't think I have it as a wet bulb temperature.
So like, I usually use the dry air and just figure it out from there. As long as you
Yeah.
don't have to, because who knows? Because you know, with the diagonal line, that's associated with the enthalpy. So I got really confused.
Yeah,
about what
no,
that line.
I'm pretty sure that the wet bulb is the horizontal line. And in your solutions for the practice exam, you have it as the horizontal line going across.
as the let me look at my solutions.
Well, I guess vertical from this direction, but
Yeah, no, I think I made that mistake previously. I'm a mistake prone individual, so this is not out of the ordinary for me. Where do I have my practice exam solutions? Here we are. Yeah, so I think I made this mistake last time. Yeah, my solutions, I do have it drawing straight down. So I think I went through and did the same material balance. So yeah, I think I botched this one, guys, for the example. So let me share this.
so which one is right? The practice exam solution or the way that you're showing it?
I gotta double check real quick.
Oh, okay.
So I did my math correctly, but then I didn't factor in the relative humidity. So I got to redo my calculation really quickly. But I think I corrected this on the exam. I think it is a straight down line here. So yeah, I got a pie in my face on this one for sure. What I'm going to do is right after this, I'm going to rework it and then verify through the material balance that it is the straight down line. And
Wouldn't the straight down line tell you like pounds of water per pounds of dry air? Like the second axis? Because there's two axes on the horizontal axis.
yeah, so I think that might be a way that we can justify which one is the correct way of doing this one. So with the, if I have a constant, so if I zoom in here. So if I have a constant amount here of the absolute humidity and I just cool it down, right? If I can draw a straight line. Then it would make sense that nothing condenses until I hit 100% humidity, right? And that would correspond to where the wet bulb and dry bulb are the same, in this case, 50 from where we draw it out in this problem statement here. Otherwise, if you didn't, because this is representing a closed system, right? So I have a box with a certain amount of water and a certain amount of air, and I just cool it down, right? I'm keeping the ratio of water to air the same, and that's exactly what's in these pieces here, right? Grains of moisture per pound of dry air and pounds of moisture per pound of dry air. So in this case here, right, it would be, it would make sense that the wet bulb should be this way. Because when I was talking through this just a moment ago, I said 60 and 55, and I think 60 and 55 is higher than 70% relative humidity. So I think it has to be this one here, which is 80%, which makes more sense. Because I would expect the dry bulb and wet bulb to be closer in temperature in that case. So I think I just totally botched this one, guys. The solutions, I believe, are correct. And I will verify that with the material balance in just a moment, as soon as we get off this. And I'll send out an email to clarify to everyone.
That makes sense. I have a different question.
Sure.
On number 5.
Of the practice exam?
Yes.
Yeah.
I was just wondering, when you're doing the P max and P min, what saturation, well, the vapor pressure do you use, the P sat? Like, how did you choose benzene over the naphthalene?
Okay. So in this one here, right? Question 5?
Yeah.
So the vapor pressure is only going to be a function of the temperature. So those values are fixed for the whole phase diagram or for the whole flash calculation.
Yeah.
And so when we're determining the minimum and maximum pressures here, they correspond to the bubble and the dew pressures. So I substituted in for the 50-50 mixture, X is equal to 0.5 and Y is equal to 0.5 in these ones.
Yeah.
And then this summation is going to be equal to 0.5 multiplied by the benzenes, which is 610, plus 0.5 multiplied by the naphthalene, which is 16.0, and that should get me the 313. Does that answer your question? So I'm using both of the vapor pressures, and I'm just using really quick notation here to show that I'm summing up this for every component in the system.
Okay.
Does that answer your
Yeah.
question? No, I'm not sure I answered it.
I think it does answer it. I think I just did the math wrong.
Okay, and then same thing for this one here, but the
Yeah,
blue one's
it's
just
a
little.
summation. Yeah.
Yeah, it's in this case it's 0.5 divided by 610 plus 0.5.
Yeah, I think I was just getting confused because
16.0.
yeah, I get it now. That makes sense. Thank you.
Good. Hey, any more questions? if you guys have any confidence left in me after my psychometric mistakes.
So, I guess for this exam, we don't have to worry at all about the enthalpy, right?
No, no enthalpies at all. Don't worry about those.
Even, or like the state or anything like that, integration.
No.
Okay.
So yeah, we've had some energy balance questions on the homework, but do not worry about those for the exam. So those are just early materials so that you can have some homework problems as we talk about it in class. But I like to chop off the exam to give everyone a little bit of time to brush up on things.
Okay, sweet. Okay.
Any more questions? Okay. Well, what I'm going to do is, so you have a question in the chat. So homeworks, definitely 3, 4, 5, and 6. Definitely feel comfortable with those. Don't worry about any of the energy balance type problems, so enthalpy calculations. But anything that's not an enthalpy calculations on 4, 5, and 6, those will all be focuses for the homework. I think there may be a small chance, let me bring up homework 4, or homework 3 rather. No, homework 3 doesn't have any phase changes. So yeah, so homeworks 4, 5, and 6, those are going to be the emphasis. All right, did anyone join us late that has some questions? What I'm going to do is I'm going to record a video and on my mistakes for the psychometric, and then just make it clear how I convinced myself that I was making mistakes. And so I'll make a video and record it on Zoom, and I'll upload it to the same channel and point everyone in the right direction towards that one. So I will do that so that people are aware, and I'm just going to avoid the wet bulb. So it won't affect anything for the exam, but I want to correct that mistake. I got a question on the chat. Any more practice tests? I do not have any more practice tests that I will be sharing. So it's just going to be that one, and the homework are going to be your resources for preparation for the exam. All right. I'm happy to stay on for a bit longer, but if there's no more questions, I might end it here. All right. Well, thank you all for your participation, and I will fix my mistakes and let everyone know, but I'll make sure that it's not going to be a focus for the exam. Okay. Take care.